Please keep thinking very hard about what are the most important questions in the topic that you have. If you would like to lead a part of the discussion today, we have free discussion and summary in the afternoon, so before the coffee break even, and yeah, the most engagement, the better. Okay, Michelangelo.
Okay, thanks. Can you hear me? Yeah, I guess so. Okay, so, thanks for the presentation, obviously. And I will continue what Carlo actually started yesterday. So he was speaking about like this defect safety, how it's working, how we can build operators on top of it, how we can compute with analytic bootstrap a lot of interesting quantities as strong coupling. But I want to remind you more or less which is our goal. This is a program that we are trying to build with Colia, Nika, and Julius that are here in the audience, and Andrea that is in Torino. Maybe he's watching on YouTube. Hi, Andrea. And okay, so our goal is to solve, so solve is a big word, but I will mention what I mean, solve CFTs that are integrable. Okay, and a prototype of what we want to solve is, for example, n equal 4 super EM means. And everyone is happy about it because we like n equal 4 super EM means. Obviously, since it's integrable, I mentioned that is important for everything I will say from now is that obviously we are talking about large n. So number of color in SUN is infinite. Okay, what I mean by solving, I mean computing CFT data. And CFT data actually are of two kinds. There is the spectrum, delta I, of all the operators, and then the OP coefficient, C delta S, structure constant. Okay, cool. And to build this program, obviously, if you read very carefully the title of the workshop, obviously I'm working using integrability. And conformal bootstrap. Let me mention again what actually Pedro was saying, that integrability is an inside view, if you want, of the theory, and bootstrap is an outside view. Indeed, with integrability we mean something like solvability of the theory, because we go very deep inside the theory, look at the operators, solve them, looking at the spectrum. And with bootstrap, one is interested to classify, and in generally solving the theory, just looking at like some constraints from outside. And what is the naive picture of this bootstrapability business is that integrability has very powerful tools like quantum spectral curve, where we can input, okay, maybe the marker is not the best, this one. We can input something that is related to local operators, indeed like quantum numbers. So we can classify which operator we are interested in. And integrability, in particular quantum spectral curve, is spitting out the spectrum of the operator we want. Actually, of the multiplet related to this operator, but whatever. Bootstrap instead is working a different way. Indeed, we are inputting some constraints, and this is spitting out some bounds for, in principle, also for delta, for spectrum, and OP coefficient. And our naive idea, let's say, is just to take the output of integrability, put it inside Bootstrap as an input. So we already solved for delta, so this one is not there anymore. And computing bound, very precise bound for OP coefficient, okay? We call this stuff bootstrapability, and we prove in some way that this is very powerful and they are very good together. So let me say what bootstrapability is this big art. This bootstrapability, or whatever is written. Okay, cool. Obviously, I said at the beginning I want to compute n equal 4 super EM means. So Simon can do it, we cannot. So I mean, like we want to be very precise in C delta S, so we try to go somewhere in which we are very comfortable. So where we compute the spectrum, we can avoid double traces, all this business of the double discontinuity, etc. So instead of working directly in n equal 4, we go in a very, very, very nice environment that is the Wilson line inside n equal 4, where operators actually are sitting on top of the line, but they don't have traces. So double traces are not there. we can compute the spectrum completely, and we are very safe from integrability point of view. Okay? And this is connecting obviously with everything that Carlo was saying. And since I will use a lot of the information that actually was mentioning, let me maybe do some kind of recap board of what Carlo was saying. Okay, I'll try my best to fit everything in one board. Okay, so we are studying Wilson lines in n equal 4 super means, and the definition, everyone is comfortable with it, I guess. We are working in the, it's not general representation, we are staying in the fundamental representation. I just mentioned this stuff now, and I will never talk about any other representation from the rest of the lecture. This path ordering exponential of the integral of I and mu dx, no, whatever, x dot mu plus some vector in 6D times the scalars. Remember, we have 6 scalars in the theory. X dot d t, x of t, obviously. Okay, we have 6 scalars. We are coupling the scalars together with inside the Wilson line. So it means that the Wilson line is not only locally supersymmetric, and we can make it globally supersymmetric, choosing a precise value for design. For example, if we are integrating along some curve and gamma is a line, n is just 0, 0, 0, 0, 0, 1. That means that we are selecting just phi 6. And doing that, then I am changing some names, the names of phi, just for simplicity after. So we have phi orthogonal to the line. Those are direction I from 1 to 5. And then the 6th direction is phi parallel, so it's the one that is coupled inside the line, okay? Cool, this is the Wilson line. Then, okay, we know about the symmetry. I'm not repeating this stuff, I'm not very tedious about this stuff, but you remember, you have the line inside n equal 4, so you have rotation along the line, you have translation. You have translation along the line and rotation around the line. And then there is also our symmetry that is preserved because the orthogonal direction are preserved, so instead of having SO5, SO6, you have SO5, okay? Cool. And since there is this symmetry that is partially broken from the original theory, we can reorganize all the operators of n equal 4 in representation of this new theory in 1D, okay? And indeed, you can build the multiplets. Carlo was calling this multiplet D. I'm stuck with the Dolan and Osborne way to call them, so they are BK multiplets, they are short. That means that they are protected. And for example, the simplest one is a B1 that we will use a lot later. And B1 is made by, the first representative is the phi orthogonal of dimension 1. Then you act with some supercharge, and you will have some spin or some fermion, whatever. And then the important one that is giving the name to the multiplet is the displacement. That is an object of dimension 2. That is very important for people working in defect theory, okay? Then you can do, for example, B2 and some symmetric combination of INJ, or yes, INJ of the phi orthogonal, then you act, and so on and so on and so on. So you can build an infinite set of them, depending on which kind of scalar you're choosing at the beginning and acting with supersymmetry. And then there are long operators that are obviously non-protected, so any element of the long multiplet, super multiplets, so any element of the multiplet has a dimension delta. And for this lecture, I'm just mentioning the long multiplets with spin 0 and Dinkin labels 0, 0. So it's also the one that actually Carlo was mentioning yesterday. And those one are the one that we like the most with integrability, because are the one with dimension that is not protected, so we can compute it with the quantum spectral curve, okay? And just a few examples. The first one, the simplest one, is the one of dimension 1, and as Carlo said, the only possibility is a phi parallel. So the one coupled to the line, okay? And then you can have you have a doublet, delta 2 and delta 3. There are some combination of phi parallel with some number, whatever, plus minus phi orthogonal, and so on. You can continue to build the whole spectrum. Okay, cool. But what we do with those operators, obviously we want to compute correlation function because we are interested at some point to compute a 4-point function and to compute the OP coefficient, okay?
Sorry,
So,
again,
yeah,
what
tell
are
me.
the indices in L downstairs?
Say it again, sorry.
The indices of L,
Which L?
of the long.
Ah, this one. Yeah, the first one is spin, and we are on the line spin is 0 for this multiplet. And the thinking labels are actually telling you, you classify long multiplets in this way. This is a representation like Dolan and Osborne kind of representation. So building correlators means that we are taking our infinite Wilson line and we are starting to insert operators inside, okay? So a position T1, blah, 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 Tn. And to be fast to write this stuff, I write it as a double bracket. Double bracket means is a correlation function with a vacuum that is not in the vacuum of the theory, is actually the Wilson line itself. Because I'm putting an operator O1, O2, On here, and this means this is an n-point function, O1 to On. That in other words is a normal, let's say, n-point function in the bulk theory with some segment that is the segment of Wilson line that is dividing operators. So 1 W from 1 to 2, and so on, okay? Normalized by the Wilson loop itself. Okay, cool. So since we want to compute OP coefficient, the strategy with Bootstrap is always the same. Everyone was saying during the lecture this week that actually 4-point function is the stuff to compute because we have a lot of information inside. Spectrum and an infinite set of OP coefficient that we can characterize using Bootstrap, okay? Yeah. Say it again. If you go zigzag, you want to see like 3 operators like this?
Yeah, like we like zigzags now, right? So if you go zigzag, where's this correlator studied?
I'm not sure, but let's say I'm I really love path ordering. So I'm fixing path ordering to be in this way, and I don't want to zigzag anything. So there is 1, that is before 2, that is before 3, and so on. So I'm really stuck, and I love this configuration. We can discuss about different configuration after. Okay, so maybe I can erase this one because it's a bit too much. So 4-point function. Obviously, as always, I don't want to compute like crazy 4-point function, but the simplest one. And the simplest one, if you see all the representation of the operators, you can choose the simplest protected operator, and obviously we go to the simplest short multiplet and the highest weight. So my favorite 4-point function is phi orthogonal, phi orthogonal, phi orthogonal, phi orthogonal. Simple as that. And we can choose a polarization. Obviously, there are 5. We choose all of them to be the same. So 1, 1, 1, 1, and that's it. What is cool about this 4-point function? There are 4 operators that are the same, and we are on a line. The Wilson line is a very interesting object because we can use a conformal symmetry and shape it in a different way. And we know, for example, that a line and a circle, they are actually the same stuff. And what it means in this context, that we have a line with 4 insertions. We use conformal symmetry, and we can write it as let me name it 1, 2, 3, 4. We use conformal symmetry, and this is becoming a circle. 1, 2, 3, and 4. And what the circle can do, can rotate. So we rotate a little bit the circle, and we open up it again. And so when we open it up again, the order of the operators changes. It's 4, 1, 2, and 3. And what it means, this is like the simplest way to see crossing symmetry, actually. Because I can OP 1, 2, and 3, 4, like S channel in this part. But I can S channel also in this side. And it's 4, 1, and 2, 3. That looks like the standard Bootstrap kind of approach. Okay? And he did in formulas, if you want. If I'm calling this 4-point function g of x, let me erase this part maybe. The drawing that I was doing before is translated exactly in g of x times 1 minus x squared equal to x squared. Can you see here? Okay, g of 1 minus x. That's it. X is the usual cross ratio. We are in 1D because we are on the line, so there is only one cross ratio, so we can forget about U and V, etc. in all the polarization. Polarization are all the same, so we forget about them. And X is the simplest cross ratio that you can imagine. X 1, 2 to 3 over 1, 3 to 4. That's it. No, 1, 2, 3, 4, whatever, but you know what is it. Cool. So, now we have the observable that we are interested in, and we can, again, using some powerful stuff about the theory, we know that it's super conformal. Say Susie. And this again is something that I'm taking from Carlo's lecture, that indeed g of x can be written as some function, f, that I'm explaining what is it, x squared, the cross ratio square, plus a differential operator, that we are not interested in what is it, and it's not important now, but just to show you the shape of it, and this new function that I'm calling reduced correlator. Okay? So this is the 4-point function, the full correlator, and this is the reduced correlator. Why reduced? Because actually this part contains all the information about the BPS part, so the topological part of the theory. We are taking out from our 4-point function, and then we focus just on the non-BPS part, if you want. Okay? This f part, indeed, can be written also as 1 plus the OP coefficient of the BPS operator passing through the OP. Okay? And again, this was also mentioned by Carlo yesterday. This is coming from the topological sector of the theory, can be computed with localization, and has a very simple form that I don't remember. Okay, here we are. That is related with double derivatives of the Wilson loop over the single derivative square. And that's it. And this is coming from acting with derivatives respect to area of Wilson loop inserted on a circle. So it looks kind of complicated, but localization makes this stuff very, very, very easy. And all the BPS part for any insertion that we are putting inside the line is related to some set of derivatives respect to the area spanned by this loop. They are organizing themselves in a determinant. They have very nice formula, etc. Okay, cool. And probably later today I will try to prove this one from a different approach. So you just using integrability, but we will see if I have enough time. Okay. Cool. Last stuff I want to say.
You say like any configuration with BPS operator, it's only up to 3-point function.
What do you mean?
You said like any configuration of BPS operators is governed by localization. It's only
no, obviously 3 points because you want to compute CBPS, you want to compute an OP coefficient. But I mean, if you go higher and higher with the BPS operator coming from other multiplet, I didn't do the computation, but I really believe that is related with different derivatives. And so you can compute CBPS of very high operator just doing a set of derivatives. This is something that we did also in the multi-correlator setup. That, for example, we compute some operator in B2, some other operator in B2, and one operator in length 4. So it's a pretty more complicated object of this one. You can just compute it with a set of derivatives. That's it. Okay, last stuff I want to mention is about the reduced correlator. Why we are very excited about this f of x? Because it's encoding a lot of information, because f of x can be written in terms of the OP. Obviously, I'm talking about OP, but I didn't write the OP at the blackboard, the whiteboard. So let me go back. Can you see here? Okay. So something that I forgot to mention is obviously that we are inserting operator on top of the line. This is a CFT that is fine. All the axioms of the CFT works, and so we can build an OP, obviously. And the OP, for example, for the simplest operators, because they are the one that we are interested in, is given in a Carlo paper. There is a selection rule that is telling you that two B1 operator very close together can be expanded to the identity plus some operator of the B2 multiplet that is starting out from length 2 plus an infinite sum, as you can expect, of the long one. Okay? Exactly those one. And you sum on all the dimensions. Okay? And then the reduced correlator actually is encoding this kind of OP. Okay? So f is a function of the cross ratio and can be written as f of the identity. Let me use it maybe capital. F of identity of x plus CBPS square f of B2 plus the sum of all the OP coefficient. Let me be precise here. OP coefficient of phi orthogonal 1, phi orthogonal 1, and some operator over dimension delta I square, f of delta I. Those capital F, this one, and this one, are the 4D conformal blocks. That is nothing else than an hypergeometric function to F1, okay? Yeah, 1D, yeah, sure. Yeah, okay, okay. Let me find some excuse to say that I was saying something about school. Yeah, super, yeah. Conformal block. And yeah, okay, they originate from the 4D conformal blocks, and then you can reshuffle them in a way that they are automatically super conformal, and they are just indeed a combination of these two F1, okay? And last stuff is that obviously if G of X is crossing symmetric, and we can expand it in terms of F, small f I mean, obviously small f will be crossing symmetric too, but the crossing symmetry is slightly different. Because instead of being equal to this blah, 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 is equal to minus itself. So simple as that. Okay. Also, this is the recap of everything that Carlo was saying that we will use during the lectures. And just while I'm erasing, I can tell you more or less which is the setup, the goal of this lecture. I'm trying to keep stuff simple, so we will stay in a configuration in which we are looking only at one 4-point function instead of a mixed setup. And so I will show you more or less which is the idea of inputting delta, the spectrum, inside the conformal bootstrap and extracting OP coefficient in the most simple way. And then how we add more information about integrability through integrated correlator or other operator of the spectrum and so on.
But it's just something very simple that
Yeah.
I got confused. You wrote that the reduced correlator is like 1 plus the BPS.
Yes.
But the G is also like 1 plus the BPS. Like, where is the 1 coming from in the?
The one is the identity, the action of they say this is just X. That is the conformal block of the identity that is present in the OP.
My question is the f of x, the reduced correlator that you wrote, is really the little f of x, or is G of x that has that expansion?
It's little f that has this expansion.
And where does the big F come from?
Big F are the blocks. So you take the 4D blocks,
On
use the symmetry.
first line of G, the big F that is 1 plus CBP.
They like mat BBF.
Yeah.
Okay, sorry. There are too many F's and G's,
Yes,
so it's a mess. But anyway, this F is a number. Is just 1 plus CBPS and is fixed by the supersymmetry. So if you're using supersymmetry on G, you see that you can write a differential operator times some blah, blah, blah. And what is remaining, you can interpret it as 1 plus CBPS. That is the same CBPS that is appearing here. Yeah. Exactly. So indeed, I'm trying to stay in the most simple case. So in principle, what I'm writing here can be extremely general. So yeah, it looks like a redundant, but yeah, because you can write this formula G of X equal F blah, blah, blah in a very, 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 very extended way for any operator of the BK kind of multiplicator. Mm-hmm. You mean this one?
Yeah. Is that both the correlation function with the polarization on and the superconformal blocks can be parameterized as written in the upper line, so with a constant and a function. Now, individual superconformal blocks are parameterized by a constant and a function, okay? It happens that all the long blocks have the constant part equal to 0, and the function non-trivial. the only block which has a non-trivial constant part are the one associated to exchange of short operators. So the conformal block decomposition splits into two equations. One is that the constant is 1 plus c squared, which is interpreted as the micro bootstrap I was mentioning the other day, which is like this kind of topological subsector of the theory. So it's really capturing a topological subsector of the theory, but still is a OP decomposition. This math BBF is equal to 1 plus c squared. And the other is what is left. I hope it's clarified.
Okay, thanks.
But the real value is that you can write any polarization of the scalator and so one function X.
Yeah, it is right, but you should never forget that you also have the constant. So it's not like you can forget about the constant and ignore it. You have that equation together with the one for...
Okay. Any other questions? Okay, cool. I guess I can move on. And okay, what I want to show you is the simplest bootstrapability setup. That means inputting the minimum amount of information of integrability inside Bootstrap. We want to extract some OP coefficient, and actually the easiest OP coefficient. Okay, and to do so, we just see this the crossing symmetric function, and we give it a name. So we know that y minus x square f of x plus x square f1 minus x is equal to 0, and I call 0 with a different name. So I call 0 v of x. It's a good name for 0. Okay, and then I can again rewrite this reduce correlator in terms of block expansion in terms of v. So that means rewriting the reduced correlator formula in a automatically crossing symmetric way. Okay, so let me do it. Is v identity of x plus CBPS VB2 square of x plus the sum of over all the delta I the OP coefficient, phi orthogonal delta I square, and v delta I of x. And this is equal to 0 automatically. What is the good stuff here? That v of 1 is f of 1 is x, so v of 1 is known. CBPS is known from localization, and is a function of g, and is exact. VB2, again, is known. Again, is a hypergeometric function with some number inside. So let me call this one v1 plus b2, and is known. And is a function of g, okay? And in this side, there is a lot of stuff that we don't know, because there is an infinite set of OP that we don't know, and all the deltas. So what is the point here? To reduce these two infinities of two sets of unknown to just one. So we input all the deltas, all means a lot of them, and we compute and we solve for the OP. Okay. So this means that we have to compute the spectrum, and to compute the spectrum, there is a paper by Collia, David Grabner, and Julius that they actually understood how to crack the first line of the spectrum for this 0,0 long multiplet, but then later they were able to compute more and more and more and more. And so just to show you a picture of it, I try to write it in the best way I can, but then later, if I have time, I show you the actual photo. Huh? Keeps? Like in the say, okay. So I need 35 of them. Anyway, the first line is starting from 1, because we know, you remember also Carlo was mentioning that there is a unitarity bound, so everything has to be bigger than 1, and so obviously we start from 1. And the first operator is going from 1 to 2. And you can imagine that this operator is exactly 5 parallel. This is the dimension of 5 parallel. Then there is a doublet that is starting from 2. And those are O2, 3, the one that I wrote here. And then so on and so on and so on. And when you go to j equal to 3, there are 6 states. There are 2 here, and there is 1 here. There are 6, and 4 of them are going Okay, this is 2, this is 4. 4 of them, they are going to 6. One of them I want to write in a different color because it probably is going to be important later. This is going to 7. And then there is one that is going to 8. And then we go to 4, and there is another one that is going to 8, and so on. You can continue. And obviously, the number of operators is growing very fast. So when you're around the weak coupling dimension, I don't know, like 6 or 7, I'm not saying that it's a continuum, but almost a continuum. So what we want to do, we want to insert data from integrability, but obviously we want to stay in the place in which we can manage them, and it's not a continuum because we need to have a gap between them. This is the big point later, you will see. But yeah, so this is the spectrum from integrability. Those are the first 10 states. We can go higher, but we can stay to 10 because we are happy about it. Okay, obviously this is done with quantum spectral curve. Kolya was mentioning what quantum spectral curve is, like QQ relation and analyticity condition on top of the Q. But I'm not going to speak about it because it's impossible at the blackboard to be precise. Anyway. Okay, so now we know the spectrum, so we have 10 deltas, delta 1, delta 2, delta 2, delta 3, for any value of j, so of g, sorry, I forgot, this the spectrum, and this g, this is the coupling, g equal to 4 pi, square root of lambda over 4 pi. Okay, cool, so how we insert this data inside here? One stuff that we notice, OP coefficient, are square, they are real, so those are positive. That is a very important condition for Bootstrap, numerical Bootstrap, because we will use the numerical Bootstrap in the numerical fashion, say. Okay? And so the strategy here is the one that was developed for the 3D easing and all the business after it. That is actually, since we have one equation with like infinite variables inside, the only way to solve it is to tune some functional to be some kind of a resolvent in some way. So we define a functional, a linear functional, and we can, in general, say that is a set of derivatives. Okay, let's call the functional alpha that is acting on some function h of x, and is equal to a sum L from 0 to some cutoff. Let me call it n there. Some coefficient, a of L, some number, and derivatives, 2L of h. And then we compute it at x equal to 1/2. Okay? So this function is a set of derivatives that we are using to act on top of the blocks. Obviously, we cannot do infinite amount of derivatives, so we have to put a cutoff in the sum, but the bounds will be still rigorous, with the cutoff being big enough, okay? And so this number of derivatives will be a free parameter, a parameter that I can tune in the numerical Bootstrap, okay? Cool. Then we impose alpha on, let me call it star, on this formula, okay? And then from this, we generate inequalities. And those inequalities are bounding by what I want to compute from this equation. Okay, so I guess I can give you the example. Say it again. Impose, like I'm acting. Yeah, I act. Act on star with alpha. Better? Thanks. Okay, so all this kind of business, it's easy for us to do because SDPB was developed. So SDPB, because this system is a semi-definite programming kind of setup, and SDPP is semi-definite programming for Bootstrap, or if you want Simon's Duffin for programming for Bootstrap, something like this. And then, yeah, it's a C++ routine that is working nicely. We know how to use it. after crying a lot at the beginning because it was hard to understand. But anyway, and then so we know which kind of input we have to put it there. But like schematically, I want to show you how actually it's working just from the back, the whiteboard. So let me rewrite this stuff as a v1 plus b2. This function, this constant of g, if you want, that we know. 1 plus b2 of x of g and x, whatever. And then I'm opening up the sum. So instead of, again, let me be a little bit more simple in the notation. 5 orthogonal delta I, let me call it just C delta I, okay? Okay, so this is the sum. I'm opening up the sum. This is starting from the first state, this one. Then there are 2 operators, and there are 6, and so on, and so on, and so on. So I'm just isolating the first operator. So this means that this is plus C delta 1 square V delta 1 x plus an infinite sum that this time is starting from 2, from the second operator, okay? Cool, so I want to solve for C delta 1. The easiest stuff to do, obviously, is to impose the function in order that is 1 on V delta 1 to isolate C. So my first condition here to make STPB work is that alpha on V delta 1 of x is a number, is a normalization. And that can be 1 or minus 1. Let's choose 1 for the moment. Okay? This means this is gone. This is 1. So C delta 1 is isolated, and we can invert the formula in some sense. But then we don't know exactly those objects, so how we can quantify more or less those objects? Second point, indeed, is acting with the infinite sum, with this V delta I. Since C is positive, we want to impose that V is positive. So we can put it in the other side of the equal, and we know that it's some positive quantity. And we don't know anything else about it, like just that it's a positive quantity, hopefully small. And so we say, this is positive. But where is positive? It's positive after some gap, because we choose delta 1 and we know where it is. But from 2 and to infinity, we don't know anything in principle. We don't know where are the operators. So let's try to don't know where the operators are and say we have delta 1 and delta 2, and from delta 2 is a continuum. So I'm saying this is positive, but from delta bigger than delta 2. Delta I bigger than delta 2, that we call delta gap. Okay? Cool. And the last stuff that we have to do is apply alpha on the BPS part. And we maximize it. And this is giving us an inequality. Let me call this maximized function on top of it is minus or plus minus B up. And this is giving that C delta 1 square plus a positive quantity plus minus B up is equal to 0. Okay? Cool. This is one condition that one constraint that we can do. But I told you at the beginning, this is just a normalization, so I can choose the other sign. And indeed, let me call this one upper bound. And for the lower bound, alpha acting on the same stuff is giving minus 1. And then the same stuff. We maximize it, blah, blah, blah. But this stuff that we maximize this stuff, this time we call it B low. And this is giving us similar inequality, a similar equation. C delta 1 square plus a positive quantity. This time with the minus, because we normalize with the minus, plus B low is equal to 0. Okay? Cool. Then we put everything together, and those two equations, they are actually defining an inequality indeed. C delta 1 square has to be less than equal than B up, but bigger than B low. And that's it. So we define the bound. So which is the most important quantity here in all this business? Is the functional. So we have to, is STBP actually what it does? it computes the functional. So we have to expand in derivatives, discretize the blocks, etc. But the point is computing the functional. And just for pictorially understand what is going on, imagine that this is G, this is the line of G, this is the coupling. We know where is the first operator. For example, this first operator at G equal to square root of 75 is here. This is delta 1. The second operator is at the same coupling is here, delta 2. And then there are many others, but for the moment we don't care about them. So, say it again? Yeah, sure. I mean, this is the line of delta for a fixed value of G. Sorry. We don't care what is happening after delta 2. And so this line, if you want, is taking the spectrum and slice it as some fixed G. And this is the first delta 1, this is delta 1, this is delta 2, okay? And so on. Cool. So I told you, for the moment, just to keep everything the simplest possible, we forget about the other operators. So all this part is a continuum. This is delta gap. And what the functional does. At delta 1, we said the functional is 1. And is decreasing, is approaching delta 2, and then is doing whatever, and it stays positive, okay? Obviously, smaller the functional, smaller the bigger than 0 quantity, and so closer C delta 1 is to be up. Same stuff for below. So the bound are shrinking if the tail of the functional is small, okay? Cool. This is what is going on. And in this way, you can compute C delta 1. We can input our data for delta 1 and delta 2, just 2 states. I want to stress this stuff. And then, if I have time at the end of this lecture, I show you which kind of plot we can build with this kind of algorithm. Okay? Cool. Just to anticipate it, just inputting delta 1 and delta 2, so 2 states, you can reach 4 digits of precision of the bounds. That means that the upper bound and the lower bound, they are the same up to the 4th order. So we are already looking at something like that looks like not an island, but a function in G, okay? Cool, but this is not enough. I mean, we just inputted 2 states. We have a lot. So why we are not inputting more information about integrability? We can do it in many different ways, but obviously the trivial one is like, we know many other delta. Let's find a way to inputting many more delta inside the algorithm. So let's go to how to input more states to Bootstrap. Cool. So taking the red. So the concept is not very different. It's exactly the same, but we have to understand what it means. For example, computing the OP coefficient, for example, for delta 3, skipping delta 1 and delta 2. What is going on top of them? What the functional does between them, for example. Or if I'm putting delta 3, 4, 5, 6, blah, blah, blah. The function has to be positive only on the operators, also between them, and blah, blah, blah. So this is the point. And the answer is actually that the functional doesn't need to be positive everywhere, just on top of the operators, because the best functional possible that you can write actually is some kind of function that has all the zeros of this function are exactly sitting on top of operators. And this is exactly solving the theory in some sense, because it knows everything. And what we want to do is just try to simulate and going closer and closer to the best possible functional, okay? So we change the algorithm in this way. It's very similar. So we stay with the normalization. This is the same stuff, 1 plus or minus 1. But what is the difference? I can write it here maybe. Instead of having delta 2 as a gap, we input 10 states. So we have delta 10 as a gap. And that's fine. The continuum is just, instead of here, will be here, delta 10. But this is not very different. The point is what is going on in the middle. Because here, we have more deltas. There is delta 3, 4, 5, 5, 6, 7, 8, 9, and so on. And what we impose? We impose an additional condition. that alpha on V delta I, so the same, this one, when is sitting on top, when delta I is equal to some delta that we know, this is positive, but just there. So we divide we have 1, the normalization, then the spectrum up to the gap that impose positivity only on the points in which the spectrum is, and then the continuum that has to be positive up to infinity. What is the advantage here? Why I'm mentioning this stuff? Because let me erase it. Okay, no, let me keep it like this. In the case of before, what was happening? That we were imposing positivity everywhere, so the functional couldn't really move much. So my intuition before this stuff was like, if we constrain Bootstrap more and the functional more, we will have better results. But this is actually not true, because if the functional is more free, can explore, for example, negative side of this picture, and this allows obviously to have a more smooth transition here. For example, you can use less derivative to approximate better the Bootstrap problem. Okay, indeed, in this case, we can have something like, you know, delta 1 is here, and there is kind of a big gap between 1 and 2, 3 that are very close. Then again, there is another big gap, for example, a strong coupling. Look at the picture of the spectrum. And then there are 4 operators very close, then 1, and then other 2, and so on. So what the functional can do, can go down, explore 2, 3, and be in positive there, but now it doesn't have to bump and go up again, and go up. It can explore and go down. It can be negative, and raise up, and be negative, and again. The most important stuff is that at this point is positive, and that's it. And doing just this simple assumption, we gain like up to 75% of the error. So there is a huge gain. Let's say the biggest gain that we have in error, I will speak about it probably later on today, is about inserting integrated correlators. But this one is already like a strong coupling in particular, like doubling the error. So halving, actually. Yeah. Yes. Maybe, yes. Say it louder. That. Okay. Is important depending on the resolution of our function, in the sense that if n derivatives is 20,000 billion times a gram number, maybe the functional can be free enough to explore and be very oscillating here and going down and up, but you don't know, who cares? But in the sense that, I mean, maybe it's not even going there with infinite derivatives. The point is that obviously bigger is the gap, higher is the possibility that the functional is exploring negative sign. And this means that obviously this transition here is way more smooth than going up and down and oscillating a lot. And this means indeed that with the same number of derivatives, in some sense, precision has to be better, because we are approximating better the functional. And if the functional wants to go negative, has to go negative, and that's it. And obviously, this is the functional that we define here. So this is a functional made with derivatives. This is not the only choice. So this is just the simplest choice. And it's the one that we are comfortable with because it's the simplest and we are lazy. So that's it. So there are functions, for example, the one that is using Miguel Paulos, etc. They are very, 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 very different, and the concept of doing Bootstrap with them is very different than this one. Okay, cool. How much time I have? I have like 15 minutes or something. I started later. Huh? Okay.
Sorry, just want to ask a similar question again. So, have you seen in practice a functional that goes negative between near points like this, like the 4?
Not in the point, not where the points are very close.
No.
This is the whole point. Indeed, like that we like when we have some kind of spacing between states. And for example, a very weak coupling is true, because 1, 2, 3, 4, 5. So the spacing is 1. A mid coupling can be true, but it's not always true. Can be the data can be very close together, and so it's very hard to explore gaps, let's say. But a very strong coupling, like Carlo said, obviously operators are organizing again in integers, 2, 4, 6, 7. Then now we will talk about the 7, 8, 10, and so on. And so the spacing is 2, for example, there. And the space is big enough that obviously a strong coupling will have a huge gain in precision. So why not? Like averaging, you mean?
Yeah, because remember in the first paper, you took average, you made some combination of the two higher OP coefficients.
Well, you can replace with two states at the beginning and the end.
Yeah, also, you can replace the beginning and the end, the opening a gap between them.
Negative, so why would you do that? No,
Yeah, but let's say,
okay. Interesting feature, though, what happens is that when we had one gap, then increasing number of derivatives was very smooth, right, in the functional. So we can actually extrapolate to infinity.
Yes.
It looked very stable, the fit. But now when you introduce all these gaps, there are some phase transitions at certain values of number of derivatives where functional can be bothered to go between the states and become negative. At this point, there is like a jump in precision. And then it carries on until it again you reach some critical value of number of derivative, and it jumps again. So which kind of makes it worse in the sense that you can't extrapolate anymore. So you should actually take.
I didn't want to mention this stuff.
Precision still
but
increases.
yeah, maybe it's important to say it indeed. And this kind of like phase transition between going negative or not is also depending on G, obviously, because it's depending how the gap is big. So fixing G and fixing the number of derivative, you can go in or not. So obviously raising the number of derivatives is easier to go down. Lowering, you don't go. And so obviously in error, you have some kind of jump. So sometimes if you see, maybe later if I have these 3 minutes at the end to show you some plots, you can see that the error, usually they are shaped like this, okay? So there is some kind of area of the G, this is G, in which is harder to explore gaps, because G is like between, let's say, 0.25 and 1 is a place in which the spectrum is not very gappy, okay? And so in principle, to explore it, you have to raise the number of derivative enough to have this phase transition and go down, but that's very painful, okay? Cool. So this was the easiest setup of Bootstrapability. Now I want to tell you something more about more information about all this business. That is the use of some symmetry that we found while we flip the Wilson loop. So remember, all this stuff is on a Wilson line. So because I'm chit-chatting a lot, but this stuff is important to repeat it. So we are on top of a Wilson line. The Wilson line has a path ordering. So it's important if the operators are ordering some way from 1 to 4, or their order is from 4 to 1. So ordering is very important. And indeed, we can explore this symmetry that obviously we call parity symmetry. And is indeed the symmetry of our observables, so our 4-point function, or whatever, our 3-point function, if you want, while we flip the Wilson line, okay? So naively, I just want to show you naively what I mean. So we have the operators, as I was mentioning before, like 4, 5, and 9. I'm just showing you the scalar one for simplicity, okay? So we know this is phi parallel. This is it's written here, phi parallel square plus phi orthogonal, the same. And this again, phi parallel cube plus other combinations that I don't remember, obviously. Phi orthogonal plus, with some numbers, there are some like a number 1, a number 2, whatever. It's not very important now. Phi parallel, phi orthogonal, minus phi orthogonal, phi parallel. And then there is 7. 7 is the bad boy, because you can immediately see why. Okay, this is very important. So imagine you have these fields that are our weak coupling representation of the fields for the first few states, and you imagine that they are inserted in the line, obviously. So you have the line, and there is a O1, for example, here, then we have others and so on. So if we are inserting phi parallel, if we are changing and flipping the sign of the line, nothing is changing. It doesn't know about it. But if we start to insert other operators that are composite operator, changing the sign of the line means that we are watching, say, the operator from left to right or right to left. So imagine to flip the fields here. Or 2 and 3, 2 and 3 because there is plus minus, and also here there is plus minus, but it's not important. You flip 5 parallel, nothing is happening. 5 orthogonal, I, nothing is happening. Same for these 3 operators, you see? They are invariant by flipping the order of the fields. But 07 is the bad guy indeed, because if you're flipping the order, there is a minus sign. So it looks like that this operator is associated to some kind of charge that we can call parity of the operator O1, and we call it 1, because it's the same, and so on for here. But this one has an associated parity, if you want, of -1, because when we flip, we get a sign. Cool. This is a naive picture, but it's just to show you at weak coupling what is happening. The point is this is holding for any coupling. It's non-perturbative, what we can say about it. And we can say a lot, because, let me erase it, because it's not very important for later. We can interpret this kind of flipping using the symmetries of the theory. For example, if we use the charge conjugation, that is a symmetry of the Lagrangian, what we are doing, we are taking a field, and the field is going to minus itself transposed. Doing this stuff on the Wilson line means trace of path ordering exponential, a mu, let me do it schematically, a mu plus a phi parallel, okay, on some curve gamma. What it means doing the charge conjugation. The charge conjugation conjugated one, is flipping the sign. So it means that we are changing the parameterization of gamma from left to right to right to left. So this is equal to trace path ordering exp integral on minus gamma, or the same stuff. A mu is going to be invariant, but phi is flipping the sign. Okay, they look different objects, but again, the symmetry of the theory is allowing me to change phi parallel to minus phi parallel, because the Lagrangian is invariant by it. And so I can flip the sign again. So, looks like that charge conjugation plus phi parallel going to minus phi parallel is the flipping the Wilson line, okay? And what are the consequences of that? That obviously on top of the Wilson line we have operators. So what is happening when this flipping is happening with insertion? So you can imagine that now we have to charge conjugate and flip the sign of phi parallel when we have operators on top of it. And what is happening? When we flip, the operator is inserted in a point. So since we are changing the sign of the path ordering, if you want, instead of going in the direction, let's say t, if the parameterization of the line is t, we go in the parameterization minus t. This is pretty obvious, okay? And so if you want, we can rewrite the action of charge plus this flipping of the sign on correlators, say O1 in T1, O2 in T2, etc. As the flipping and the flipping of the loop. So we look the loop in this other way around. So we start from n, but this time on minus Tn, and so on up to O1 of minus T1. But any operator has to be substituted with this charge conjugation plus flipping version that we call the parity version. So O is going to OP, and OP is some number, the number I was showing you before, times the original operator, okay? And so for any operator, we have to take in account this kind of eigenvalue, P1, P2, etc., Pn. And they can be either plus or minus 1, depending on which operator we are looking at, okay? Okay, look, this looks like a kind of obvious in some sense, but has a huge consequence. Why? Sorry. The big consequence is actually when we look at, because if we are inserting 2 points, 2 operators, nothing is happening, because we can flip it and looking from left to right to left, nothing is changing. But when we insert 3 different operators, for example, this is important because order matters on the line. So it means that if we are looking at 3-point function, C of operator O1, O2, O3, all the 3 are different. because of the parity, this is going to be written as parity of the operator 1, parity operator 2, parity operator 3, times the OP coefficient that is flipped, O3, O2, O1. That's it. Why this is important? Because in a Bootstrap setup, we are halving the number of unknown. So we know that some OP coefficient will be written just knowing if these 1, 2, and 3 are plus or minus in terms of something else. And that's good enough. But the cool stuff is actually when we are going to the simplest setup, our setup of before. So when all the operator of the external, our 4-point function is written by 4 operators of the same kind. So it means that, for example, O1 and O2 are the same. And what is happening when O1 or O2 are the same? It's happening very interesting stuff, because when are the same, O1, O1, O2, just because of cyclicity of the loop, because again we can close it on a circle and then rotate it, this is automatically true. Okay? But also we can use parity. So see O1, O1, O2. Okay, let me go here. Want to be precise, don't want to do mistakes here. Is a P2, P1 square, C O2, O1, O1. But obviously P1 square is a minus 1 square or plus 1 square. So this is gone. And now we can use the previous condition. So the previous formula. So it's P2 equal to the same operator that we started with. And this is clearly a huge constraint, because it's telling us that the only operators that are passing through the OP when 2 external operators are the same are the ones that have P plus. Because if it's minus, it's not allowed. What it means? That if we are going back to the naive example that I was giving you at the beginning, you were saying that O7 has a P that is minus. And that's cool, because it means that the red line here is actually in the spectrum, but is not passing in the OP. So we can erase it, we can forget about it. And we can eliminate it from the spectrum. You can just do Bootstrap without thinking of this object to exist. And this is non-perturbative, so this is true at any coupling. What is important? The Carlo was seeing from, for example, supergravity implication, etc. This stuff from strong coupling. I would say, like, we know that a very, very, very strong coupling, lambda actually infinity, our operators are organizing in even integers, so 2, 4, 6, 8, and blah, blah, blah. And what we see from our side, from integrability, that all the states that are going to our odd integer strong coupling, they actually have a parity that is negative. So this means that is an exclusion rule for an infinite set of OP coefficient. This means that C, O1, O1, and P odd operators, all these kind of OP coefficient are 0 at all loop. And this is very powerful. Why I'm saying all loop? Because of we have an integrability way to compute P non-perturbatively, using Bethe ansatz, QSC, etc. Obviously, it's not something I can show you at the blackboard, but it's not just a weak coupling statement, it's a all loop statement. So we can say very easily that this is true for any, for all loop along the whole spectrum, okay? Cool. Obviously, there are other implications. How much time I have? 10 minutes or something, or 5 minutes? Okay, cool. So maybe I can anticipate something I wanted to say tomorrow, just to have more, tomorrow, like later, just to have more time later. And I can, tomorrow is Saturday, okay, if you want to come here, I can continue, but there is actually another stuff that I can say, but since I'm not talking about mixed correlator setup, is not very on topic, but just to say that charge conjugation is not the only way to flip the sign of the loop. You can change the sign of the loop also doing complex conjugation. So, and if you are mixing together complex conjugation and parity, you have additional constraints. And those additional constraints are telling you that some OP coefficient, instead of being 0, they are just purely real or just purely imaginary. Okay? And that's cool, again, because in a mixed correlator setup, a lot of the OP coefficient, you cannot fix them to be purely real or pure imaginary. They have to be complex. That this means you have 2 variables instead of 1, the real part and the imaginary part. But now we are halving again the number of variables. So this parity, this parity constraint is a very, 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 very powerful from the point of view of Bootstrap. Okay, so last stuff I want to mention, since, don't remember, maybe it was Kolya that advertised it yesterday, is about constraining instead of Bootstrap to give you OP coefficient to give you a combination of them, okay? So, we call it bootstrapability for linear combinations. Okay, cool. Why? This looks weird. So if we can compute all the C, why I have to compute also a combination of them? Because a combination of them can be very, very, very nice in the sense that some OP coefficient can have a very big bounds, but some combination of them can be extremely narrow, okay? And in particular, there is a very, very special combination. You can imagine which one is it. Is the full 4-point function, because you can combine all of the OP coefficient and with the block, obviously, and this is giving the whole 4-point function. So, for example, let's say, in some sense, this, in other words, means how to bootstrap g of x or f of x directly, okay? So to do so, we choose some combination that I'm calling T of OP coefficients times some functions, some function that I'm calling with a different name, but is actually containing the blocks, okay? x0 is a point, because I don't know how it's working for any x. I'm fixing x to be, I don't know, square root of 7, and then I'm computing the combination for that value of x, okay? And I just want to show you how to modify. I erased it. Okay, the previous equation that we liked, the one with v, so v identity plus b2 plus the sum of delta I c delta I square v delta I equal to 0. This is the bootstrap equation, no? So this is the equation that we liked before. How can we modify this one to actually fix constrain a set of OP coefficient instead of 1? Okay, just 2 minutes. 1 plus b2 plus the sum, we said, no? But again, I'm doing the same game of before. I'm opening up, so I'm taking C1 to be isolated from the sum. So it's C1 v delta 1 plus the sum starting from 2. I square v delta I equal to 0. Cool. And now I can, let me change the marker again. And now how we can isolate the C1 square, not as before, because I don't want to apply the functional now. I just divide by v delta 1, so simple as that. Okay? And now, what I want to compute is actually this t. Where is t? It's not there, so I'm putting t inside. So plus minus t over h of delta 1 to be the same of this one. And if you are expanding this plus and minus, you are obtaining a new bootstrap equation that we tweak it a little bit to have some this t, this combination inside. And let me rewrite it as a v1 plus b2 over v1, this object here, that is still the BPS part, plus t over h delta 1. Obviously, again, h is computed to some point. Those are function of x. This is a function of, this is a number, okay?
Sorry, I'm confused.
Go.
Why is it 0?
What is 0?
This is what you know, the previous line. No, but then you added plus minus t over h.
But 0 plus 0 is 0, no?
But it's not 0.
Why is not 0?
Because that's what you want to bound, no?
No, it's 0.
T is 0.
But I'm summing and subtracting the same object. It's like a 0 plus 1 minus
you
1.
adding and subtracting.
Yeah, sure. So, and then what is remaining here, that is starting from 2, is the whole part, v delta I over v1 minus h delta I over h delta 1. Again, those are function of a point, so those are numbers. Cool, and this is equal to 0. And that's it. So we can play the same game. Since we want to compute this combination, now when we apply the functional here to 1. So we impose alpha 1 equal to 1 or minus 1. And we do the same game as before. This time we are not constraining C1, but we are constraining an infinite set of them. And this is exactly giving g of x. So you can compute directly the 4-point function using the same, exactly the same algorithm of before. The only stuff that I have to mention, that why this stuff is a bit tricky, is that this combination, when you're imposing positivity here, usually you're imposing positivity, expanding the blocks as a polynomial, and then acting with derivatives. And what is happening? There is an exponential there, an exponential decay. This exponential decay is positive, and we put it in some prefactor. It's a number, so who cares? This time is unfortunate that this part and this part, they have different exponential decays. So this one is the one of before, the same, and we can put it away. But this one is still there. So we have, in SDBP, if you want, we have a polynomial plus some exponential e to the minus whatever, beta x, beta delta, sorry, some times another polynomial. So what we do there, because SDBP is not very happy about two exponentials at the same time. And what we simply do is we do an approximation in the sense that, again, what Bootstrap does is the infinite line of delta. Bootstrap gives positivity from a gap. So we impose positivity from a gap, and this is still the same. Before we were saying that we have the operators here, no? And we are imposing positivity on top of that. Now what we have? We have a new part of this interval. There is an interval here, sorry. We have a new interval here, where the exponential is actually having a role. So from up to infinity, the exponential is so small that it's less than our error, so we don't care about the exponential. So we can drop this part. But in this interval here, we care about the exponential. And then what we do? We do some kind of Padé before, then we did some Chebyshev approximation. And we managed to have a good approximation for the whole strip, for the whole segment, inside our error tolerance. And then plug in everything in SDBP and run it, blah, blah, blah. There will be some picture later that we show you. We can compute g of x and f of x for values of x, 0. Sorry if I was late.
Okay, let's thank Michelangelo.
Thank you.
And we have time for one question or two maximum, and then we'll go for a coffee.
Don't be shy. Say it again?
I missed what h is.
Ah, sorry, obviously, I was a bit in a rush, I didn't tell you. H is a function that depends on what you want to compute. For example, if you want to compute g of x, is the block f delta I plus its derivative. If you want to compute the reduced correlators, it's just the block f delta I. So it's just the block h, computed in one point x0. But if you have the derivative together with it, you compute g of x. If you don't have the derivative, you compute the reduced correlator.
Okay, so I guess we are going for the coffee. Let's thank Michelangelo again, and we see each other at the usual time.
derivative of t mu nu is not 0 anymore. Now we can write it as some operator in some point. Let me call it d, and you will see why, but it's pretty clear from the discussion before. X parallel means that it's inserted along the line. There is an index because we have 3 of them, and then delta of the orthogonal directions, but whatever. So you can recognize this object here, because this is the displacement operator. So it's the last operator appearing in the short multiplet, the simplest short multiplet. An object of dimension 2 is a protected object, and we really like it because it has a lot of implication on the defect. Why we like it that much? Because saying that we are breaking translation and inserting in the line the displacement operator means also deforming the Wilson line. So the Wilson line that we started with has a coupling with the scalar that is n, and we can try to modify, tweaking this n, and see what it means inserting d through changing, for example, the shape of the line. We can make it wavy, for example. So if the Wilson line is originally this one, we can do a little bump, and this little bump, let me call it this bump delta x in the orthogonal direction. In a position, let's say the position of this bump is at position x whatever, x parallel in this sense. And it's exactly the point in which we are inserting this one. This stuff is equivalent. So this is more or less the same. Why? Because I can do the variation respect to this x of the log of the Wilson loop, or the Wilson line. And this more or less can be written as a double integral. Why a double integral? Because obviously if we are, the line is a one-dimensional CFT. If we are putting one operator, this is automatically 0, so we have to put 2, okay? So T1 and T2, where T1 is bigger or is bigger than T2 because of path ordering, okay? So there is a precise order in which these operators are entering in the line. And then we have the insertion of this displacement operator in the position T1 and the position T2. Delta x orthogonal, delta x orthogonal, I and j, di and dj. Cool. So we have conformal symmetry. We are on a 1D CFT, so it means that the two-point function is completely fixed by symmetry. So we know that this object here, like usual, will be equal to some number. That this time we cannot put it to 1 because this is a dynamical object, knows this two-point function has some information inside. So this CD will be a very non-trivial function. It's not just a number that we can rescale it to 1. Over T1, 2 to the dimension of the operator that we know being 2. So this is 4, okay? And delta ij. Cool. Nice. Simple like that. But the point is that this is not the only broken symmetry, because we can break, for example, the R-symmetry current, because remember, when we have a line, we are selecting in SO6 one preferred direction. Is the direction of phi parallel, so phi6 in this case, you remember here. So we have 5 orthogonal operators that are preserved, so 5 orthogonal directions that are preserved and 1 that is broken. And so we can break in R-symmetry. We can study how the R-symmetry current changes because of the defect. And again, we can write J, the R-symmetry current, J mu orthogonal, whatever indices, but it's not very important. The important stuff is that, like the stress tensor case, this will be proportional to another operator. And you can guess what is it, because you see, this is the displacement, is part of this multiplet. You can guess that indeed this is a phi orthogonal, I, times some delta function. And again, these are, let me be precise, this displacement. And this is what Carlo was calling tilt. And this is very cool because they are part of the same multiplet. So the multiplet B1 is the multiplet that actually knows about the deformation of the line. So the tilt, R-symmetry deformation, is related to this broken charge, this broken current. Then you act with Q. Then there is another deformation that is fermionic, we don't care now. And then with another action of Q, we go to the displacement, and this is related with the broken translations. Okay? Cool. So there are 5 of them, obviously, because there are 5 orthogonal R5. So we have 3 displacement and 5 tilts. Okay, cool. And this is related. We can do the same game there. What is in terms of deformation of the line? We have the original line with some direction, and at some point at the position t, we say the. Let me write it like this. The rotation in the space n, so the SO6 space, in the 6-dimensional space, is different before and after. So we can, for example, say we have some phi here, and here we have a different phi prime. And you can also think about this stuff like an insertion of a flavor-changing operator. So the line has some flavor before, then there is a point, and it's changing flavor up to infinity. Say it again? No, I like n because it's this n. Then, if you want to be very precise, you can do a precise deformation that is depending on an angle, and I will speak about that in 5 minutes. Let's be general. In principle, n can be whatever you want. You can change it in the way you want. Then you're interested to make it supersymmetric globally, and then is proportional to theta and some angle and blah, blah, blah. Give me 1 second, I will go there. Let me repeat the same game. So we look at the variation, this time respect to this change in n of the log of w. And this again is, if we are inserting operator, one operator is 0 because of conformal symmetry, we have to insert 2. So the variation is proportional. At the second order will be a double integral, dt1 and dt2. Again, t1 is bigger than t2 because it's important the order in which we are inserting operators. And this time is the 2-point function inserted in the line, the phi orthogonal I in position t1 and phi orthogonal t2 j, delta n, whatever. Again, same game. These are 2-point function in a well-defined CFT, and so will be proportional to, again, to some number that I call this number C phi orthogonal. I'm sorry that I'm using C because this is not OP coefficient, it's just a number, so I can, let's stay with C, because otherwise I cannot read the notes, but remember this is not OP coefficient, obviously it's a 2-point function. Delta ij over t12, and this time the dimension of the operator, we know it from there, the dimension operator is 2, so t12 square. Cool. So, usually when we see CFT and we have deformations, we have some very precise operator that we can insert, and they have some very precise dimensions, etc. We can ask how the RG flow is working, so how this CFT works from RG flow point of view. And so we have the displacement operator and the tilt that actually acts, and also the identity, because we have an operator that is the identity, that is obvious, that is a dimension 0 operator. So from RG point of view, we can say we have a relevant operator, that is the identity. Then we have the marginal operators that have the dimension the same of this space-time dimension. We are in 1D CFT, so the only marginal possibility is this one. So the tilt, we have 5 tilt are the marginal operator. And then we have an infinite set, so this one, those are 5. And then we have irrelevant. And irrelevant are all the other operators, and they are infinity. Okay? Cool. Nice. So this is a very general picture. This is true all the time for any defect. This is not depending on the line. You can do for a defect of dimension, codimension, whatever, codimension 1. So it's very general. It's just looking at the symmetries. Okay? But now what I want to do, I want to connect this stuff with integrability. And the trick that we use is a very common trick. Many people use it. I mean, we can study a setup that actually has both of the deformation that I'm talking about. So both the translation invariance broken explicit, so some change in the shape of the loop, together with some flavor changing in the line. And this is my favorite stuff ever, cusped Wilson loop, Wilson line. Indeed. We have some line up to some point, let's say that this is 0, and then a second line, a second ray, that has a angle respect to the first one. Let me call this angle phi var phi, so that is very different from this phi, but I'm sorry if I will write it at some point in the same way. But I mean, this is a Euclidean angle in space-time and is related with the bump. This is a bump, if you want. This is the direction. We are doing the bump, so we give a kick to the loop and we change direction. And then we can change the flavor. So we can say, here we have some coupled scalar to the line, and here we have another one. So our choice is phi parallel here, like the normal Wilson loop. And then in the second side, we can choose n. If you see the first line on the first board, we can choose n to be something else. And the minimal choice, the nicest one, let's say, taking in account that we know, for example, other globally supersymmetric Wilson loop, like a latitude, etc., that have a similar shape, we can include a new angle, that is theta. And we can say that here we have cos theta, phi parallel, the same, plus sin theta, phi orthogonal, and I choose one direction, for example, 1. So this means that theta 0, our symmetry deformation is gone. Phi 0, also the other deformation is gone, and we are back to the original line, okay? The supersymmetric 1/2 BPS 1. Okay? Cool. This object is very well studied, and we know how it diverges, because we have a cusp, this object diverges.
So maybe you managed to confuse, maybe you can use var phi for angle and normal phi for fields, just a suggestion.
Eta. You like eta?
Already use normal phi for fields, but now you switch to var phi. It's just like circle with a stick, you know what I mean? No! Okay, yes, but then it's var phi, then it doesn't make sense.
Okay, let me do it this way. Phi tilde is fine for everyone? That is an angle.
No.
Phi tilde? No, come
no,
on.
Just instead of this fields, write like circle with a stick, you know?
No, I understand, but can we avoid
everyone
this stuff, please? So we can discuss about this stuff now. I will change it, but then
look,
in the next blackboard it will be the same.
On different blackboards, you use different notations. So just like the circle with a stick is the best.
Okay, everyone is happy now? No, I'm joking. Okay, everything will change anyway in 5 minutes again. So, W-cusp, we know how it's diverging. This is a very well-known formula, and this is an exponential. Minus, we have the log of some cutoff. Let me call it, how we call it here, T and epsilon. So T is a UV cutoff that is, let's say, shielding the fact that the line is infinite, and epsilon is some kind of regularization cutoff that you put around the cusp. And this is proportional here to a very famous object that is gamma cusp. Gamma cusp is a function of G, and in principle, in our case here, is a function also of theta and phi, var phi, okay? Cool. So gamma cusp is like an anomalous dimension of this extended object, of this non-local operator, okay? And we know...
But it's not the gamma cusp, well, it's generalized gamma cusp.
Yeah, this is the generalized gamma cusp, if you like to be very precise. Cool. So it's not the gamma cusp that is appearing in amplitudes. This is the general one, and when you want to go, for example, if you want to have the gamma that is appearing in amplitudes, you take theta and phi, they have to be equal to I infinity or something like this, and you go in the null direction, let's say, okay? You confirm? Cool. Nice. So this object, we can expand it and see, for example, when this deformation that we are taking in account are very small, okay? So phi, var phi very small and theta very small. And this is proportional to theta square minus var phi square times a function that we love, or I love, and is the Bremsstrahlung function. So it's the energy of the emitted quark. So imagine this stuff like a very heavy quark. Actually, it's a W boson because we are in unequal 4 that is propagating here, is getting a kink here, and this factor that you are changing is like a Brestlalon process. So this is the energy that is measuring this change. Okay? Cool. B. Why is beautiful? Because it's known. There is a paper by Maldacena in which they are doing a lot of discussion about this stuff. And we know that B is actually equal to lambda, the coupling, the derivative with respect to lambda of the log of the Wilson loop. That's it. Simple like that. And so is a Bessel function. Wilson loop is a Bessel function, and Brestlalon will be the ratio of a Bessel function, is I2 over I1. Okay? Cool. Now we want to see, for example, why I'm mentioning this stuff, why and how this is related to the deformation that I was mentioning before. So what is the general idea? The general idea is that if I'm taking a, this is the general picture, but I can go to a very specific setup. For example, I'm taking a line from minus infinity to infinity, and then I'm turning on the theta angle, so the deformation in theta, just in a segment. So I have theta here, and no theta here, and no theta here. This is a position, I don't know, like minus t over 2, and this t over 2, and it's symmetric through 0, okay? So this is the same of this one. It's exactly the same. Simply, instead of having one cusp, we have two. And so this will be proportional to the same stuff, but with two gamma cusp, okay? Log, etc. And so we can expand it in the same way. And this will be, if we expand, more or less, important stuff. You see, this is a straight line. So we are putting phi equal to 0. Since, you see, since phi and theta are entering in the same way, I'm not interested to keep both of them all the time, because phi on means a change of shape, and so integrals are harder. So I prefer to have a straight line and a change in our symmetry. So imagine that you are putting always now phi equal to 0, and you keep theta on, okay? So, and then this will be proportional to 1 minus 2 theta square, the Brestlalon function, times some log, plus corrections. Cool. But now we can go back, for example, here, and see that this is the same stuff of doing the variation respect to the deformation in our symmetry, okay? And so we can rewrite, I can rewrite the same stuff, dn log w. Now I will be more precise, because it's important where the cutoffs are. dt1 minus t over 2. Sorry, but this is important to mention precisely. T1 plus epsilon, t over 2. So you see, T2 is bigger than T1, so they are path order, so T1 is appearing always after T1, but we have this some kind of a hard shell regularization. So we are not allowing the point T1 and T2, while they are moving, while we are integrating, to touch themselves. Okay? Cool. And so, starting from this formula here, we know that this integral contains a constant, some term T12 square, and so I'm plugging back in. C phi orthogonal. It's written in the same way, yes. T12 square, theta square, plus corrections. And we can compute the integral. This integral is super trivial to compute. But there is one point, and there are divergences, obviously. And we try to don't see the divergences in 1 over epsilon. We look at t over epsilon. We say, like, who cares about them? And we just look at the log divergence. And we try to match the log divergence of this expansion with the log divergence here. And when you do this computation, you find that the log divergence of this integral is minus phi orthogonal theta square log. So the final answer is that we can fix C phi orthogonal. Okay? So just looking at the cusp deformation, knowing this very general symmetry discussion, we can fix C phi orthogonal to be equal to 2 Brestlalon function. And this is an exact function of G. That's very nice. Cool. Maybe some of you is not surprised, because this is a very famous result. But let's say we can do the same stuff for the displacement operator. It's simply more difficult. because the integral is 1 over t to the 4. The integral is a bit more difficult, but the setup is similar. Instead of computing something with a deformation in theta somewhere, we just do the bump, indeed. We just parameterize it, do an integration on this deformation when it's tiny, and we obtain a similar result, where this time c of displacement, so this quantity here, is 12b. That's very cool. Why is that cool? Is that cool? Because this is universal. It's not depending on the theory. So it's always true that when you have a defect, always, in any dimension, any theory, that the 2-point function of the displacement operator is 12 times the Bremsstrahlung function, the same number all the time. And this, again, the same stuff. The tilt operator in any theory will be proportional to 2b, always. And so this, in principle, is integrated correlator. Why? Because what is an integrated correlator? I'm writing here, I'm trying to finish the whiteboard here. Means that if we are integrating dt1, dt2 of the displacement operator, and we regularize it in some way, let me say it like this to be a bit schematic, this is equal to 2b, and this is also equal to the same deformation in theta, dt1, dt2, 2-point function of the tilt. So, and why I'm saying that integrability is behind it? Because actually integrability is fixing exactly this value of b. This b can be computed also via localization, because this is something I didn't tell you. This object here is not supersymmetric only when theta and phi are exactly equal to 0. There is another BPS point, and when theta square is equal to phi square, you can see it from there. And so, when we go in this limit, we can expand it. It's a near BPS limit. We can use localization and fix b. But this is true also for QSC. QSC can be built for this extended operator, and b can be computed exactly using quantum spectral curve. So integrability knows about this b. And what I'm writing here is indeed the fact that integrating some correlator of some very specific nice operator, BPS operator on the line, is fixed exactly by integrability, if you want, by a function that is known exactly in G, okay? Cool. Maybe it's time to erase here.
Can I ask a question? So
sure.
If theta is equal to phi, so then that term in front of b is 0. So how does that fix b?
If theta is equal to phi, sorry?
You said that if you set theta equal to phi, then you can fix b. But I don't understand, since then you have 0 in front of the b. So how do you know?
Yeah, this is all the definition, the fact that we go back to the BPS situation, no? So the line is has no anomalous dimension, if you want.
No, just the observation that in near BPS limit, where you're close to exact BPS,
yeah?
There is simplification in quantum spectral curve.
Yes.
You can do calculation.
Yeah, there are the big simplifications. A lot of p function and q function are equal or going to 0, and so you can exactly compute this stuff. It's the same kind of difficulty that happen to compute, for example, the slope function, where the simplification of QC is drastic. Obviously, integrability, since it's very powerful and here to advertise how cool is integrability, can do more, in the sense that you can compute highest order, or can, for example, compute the same b, the same Bremsstrahlung function, when I'm inserting on the tip here any operator that I want. So we can have more from integrability. This is like a minimal setup. But I will be back on it if I have time. Okay. So I have to remember what I wanted to say. Okay. So indeed, I was saying that integrability knows more, and let me show you why. Because gamma cusp, theta phi,
is it clear that the divergences will exponentiate? Can you get more constrained by requiring that you have exponentiation of the log t over epsilon when you go to higher orders, or is not something really interesting?
Higher orders, you mean in the expansion in theta?
In theta, yeah, in the deformation.
Okay, what is the point of the whole lecture is that at the end I will show you what is happening at theta to the 4. Okay. But there is no information by okay, there is information. There is a part of the leading term that is appearing obviously also at the highest order, like B again, and then there is a new function. That is the one that I'm showing you now. So, but the next order is not just simply the exponentiation of the one before, because we are looking at gamma cusp, not the Wilson loop itself. So we are interested in the expansion of gamma cusp itself, not the Wilson loop. So we don't care about the much, about the fact that the Wilson loop is exponentiating. Okay. So remember, we are lazy, so we don't keep both of the angles. One is 0. So gamma of theta, we said, is proportional to B. But this time, let me expand in a different parameter, in the sense that the there was very cool to expand in directly in the angles, but it's more convenient sometimes expanding directly in sine theta, okay? Because you see it's proportional to some operator, so expanding in sine theta means exactly then inserting phi pi, so phi orthogonal. So we can rewrite the expansion in this way. Sine theta square plus B again plus C over 4, yes, sine to the 4 theta plus corrections. So B is this infamous function that I was mentioning, Brestron function, and C is a new, very complicated but exact function that we call curvature, that can be written as a double contour integral of a crazy kernel. Like this kernel here is like 1 page long in LaTeX with harmonic sums, hyperbolic functions, Bessel functions. It's a crazy stuff. So it's impossible to compute it in a closed form. At least I cannot. I don't know. Or even maybe there is no paper enough in the world to write the answer. But the point is that we can expand it as small g and large g. I just want to show you what actually looks like. For example, at weak coupling. This is something that starts as a g to the 4, okay? Plus, we start to have zeta, Riemann zetas, okay? G to the 6, and so on. And at strong coupling, this is actually divergent as whatever, a number, divergent as g, plus, again, some term that is proportional to some Riemann zetas. Plus corrections, okay? So it's very different from the Brestron. The Brestron is just Bessel over Bessel. You expand is like g square over 8 plus g to the 4 over 16, some numbers. Here is way more complicated because we start to have multiple zeta values and crazy stuff, okay? And that is very common in integrability computation. This is a very strong, signature on the fact that this kind of object is captured by integrability, okay? Cool. Okay, then, knowing this stuff, one can ask. We expanded at theta square, and we found that...
So, just to say, so in this integrated correlators coming from localization, it seems also similar integrals appear.
Yeah.
A bit simpler looking, but also like double integrals of the same type.
Yeah, thanks. Okay. What I wanted to say that you saw here, like we integrated a two-point function, and this is exactly equal to a known function of g. Same stuff for the tilt operator. And this is expanded at theta square. So since we know gamma cusp up to higher order, like theta to the 4 if you want, you see here, why we don't try to do the same stuff at order theta to the 4? So this is the whole game of our proposal for integrated correlators. And indeed you can do it. And which is the nice stuff? Maybe I want to write it nicely, this stuff. I'm erasing the expansion because it's not very important. What is the big point here is that we can write two independent constraints. Let me call it constraint 1 and constraint 2. And this is the integral from 0 to 1 of that. I will explain everything that is in this formula, so give me the time to write it. G of x 1 plus log x, so I change the font again. G over x squared dx, and the integral 0, 1 delta f of x over x, and this is equal exactly to 3 times the curvature function plus the Bremsstrahlung, minus, over 8 times the Bremsstrahlung square. That's it. And this one is a c, curvature again, over 4b squared, plus f, that I hope you recognize, mat bbf, minus 3. Cool. So those are our lovely integrated correlators. So what is G? G is exactly the 4-point function that we are studying. So this object here. So the insertion of the simplest 4 BPS operator in the line. F is the version of G reduced. So is this object here that contains also the OP expansion, okay? And delta is just a regularization. So delta means that actually, let's say delta H is H minus H at 3 level. It's just a regularization, so it's not very important. But the good stuff is that we have 4-point function times a kernel equal an exact function of G captured by integrability. Reduced 4-point function times a kernel, 1 over x, equal, again, to objects captured by integrability. Spoiler, also f is captured by integrability. Yeah. We said before that it's captured also by localization. But again, localization and integrability on the line are very intertwined. Okay?
Michelangelo, sorry.
Yes.
How do you know that why should I not think they should depend on the higher function that can appear when you expand this to higher order in
but because gamma, you see, this is proportional to theta to the 4. And since theta is proportional in your action, let's say, in a path ordering exponential, theta is proportional to phi orthogonal. What we are computing here, a 4-point function. 4-point function means 4 derivative respect to theta, so means theta to the 4. So we are comparing theta to the 4 expansion of the cusp. Will be more clear at the end, I hope, if I have time to show you a bit of details. But I mean, the theta expansion of the cusp at order 4 is the same of integrating this object here. Delta G with a kernel. The kernel is popping out when we are doing changing of variables, so it's not very important. And this object here is indeed what is in the right-hand side of the cusp. So the cusp is in the right-hand side, despite theta to the 4, there is Bremsstrahlung and curvature. Okay?
So,
cool.
Small. Just yeah.
Well, sorry.
Yeah. By the same arguments, like if you're going to like 6 points, right?
Sure.
Then you have to go to sign.
Exactly.
Like what is known about integrability results for the later?
Kolja, I guess we don't know exactly the 6th order, no? But in principle, we can. If you want to compute it, please do it. I guess I skip it.
I mean, it's less explicit, but you can compute the same. Weak coupling is always easy. Strong coupling, you can just take fine theta fixed and compute numerically with any precision, if you like.
But naively, I would say, if you go to theta to the 6, there will be some new function, or maybe you can do also numerically. Maybe you are interested in some very precise G, so you can do it. There is something here. You want to do 6 derivatives to have phi orthogonal. And instead of having one integral in the cross ratio, sorry, I forgot, but I was thinking I was kind of understood that x is the cross ratio between 0 and 1. Maybe you have more. You have like 2 integrals or 3 integrals, I don't know. But in principle, yes, you can build a higher constrained integrated correlator up to the order you want in principle. Okay, so why we are talking about this stuff? Because depending if you look at what I explained before in the first lecture, numerical bootstrap will have a huge gain inserting information by those integrated correlators. So remember, what we were doing before, we are fixing G, and for some G, we are trying to find the bounds of some OP coefficient. And what we have here, here we have a function of G, we put G inside, and this is giving a number. And in this other side, we have G and F, and what we can do, we can expand G in terms of F using this formula, okay? But then F, we know that is written in terms of blocks. So we plug everything inside, and we do the integral. And what does TBP want to have? Want to have some blah 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 equal to blah 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 in terms of blocks. So we are expanding in blocks, we are inserting in SDBP, and we crank SDBP. And the gain is huge, like we are talking about 4 or 5 digits of precision just for inserting the 2 of them. If we are inserting one of them, we are gaining like 2-3 digits, but the 2 of them are extremely powerful, okay? And like just to be schematic, in SDBP, I'm surprised by this stuff, because when you are adding, when you are asking to SDBP, please solve me this problem with this, for example, with this crossing equation and so on, you are actually asking, indeed, how is made this function to be optimal and blah, blah, blah. And what it means? It means that you have a set, a list of derivatives. So the first derivative of the block, the second derivative of the block, and so on, up to and there. You remember this the parameter that is cutting at some point a cutoff on the derivative order. So you have and there derivatives, so and there information you are inputting inside SDBP just to have the all the stuff I was showing you in the first lecture. This one to me is some kind of crazy, because you are actually adding 2 parameters here, let's say alpha and beta. That is the value of those for some specific G. So just adding 2 numbers here, you gain like 5 orders of magnitude. So this is kind of magic for me, but yeah, this is just a comment. Okay, so that's the end, if you want. If you are interested in numerical bootstrap and integrated correlator, how can we implement it and crank in SDBP and have a result.
So what you are saying, so crossing is infinite set of equation. It looks like we just added 2, so who cares, right?
Yeah.
But, you know, some equations are more important.
Exactly. So let's say if you want to give a value on the importance of equation, all the information by crossing is value 1, repeated many times. But those one are just one equation with value 3 million. Okay? Cool. So in principle, now it's done, if you want, like my storytelling. But since is a very good opportunity to be a bit, go a little bit more in detail. I want to try to show you the logic of how to prove those constraints, okay? And so it's very hard to prove independently constraint 1 and constraint 2. So there is another way around, so we can combine them. If we do, for example, constraint 1 minus constraint 2 and constraint 1 plus constraint 2. There is a number between them. Why? Because, for example, if I'm subtracting the first with the second, if you are adding, if you are multiplying by some number, you can find maybe a combination that doesn't have C, okay? So doesn't have ugly multiple zeta values, contains only the Brent-Strahlung function. That in principle is a easier combination. And this is the first one, so if I'm putting 2/3 here, this is proportional only to B. So will be this one minus this one equal to some number times B, no curvature function. This other way around is proportional to everything, B and C, okay? And so, in principle, we can compute the 2 of them and prove the existence of the 2 of them to prove the 2 independent constraints. So the first one, in a paper by Nadav collaborators, was proved to be true, with a nice geometrical vision on the conformal manifold. They were computing the zamological matrix. Just one sec. They computed the zamological matrix and then the Riemann tensor. And computing the Riemann tensor, the Riemann tensor is actually proportional to this kind of 4-point function, and they were able to prove that constraint 1 minus constraint 2 is equal to what is supposed to be. Okay, so this one is missing, and this is the one that I want to try to show you how to compute.
Yeah, sorry, you say MZVs, so you do expect that there are multiple zeta values in your...
Good point. I don't know if you, I don't know.
Okay. So
but we know that it's single valued for some theorem, or they can appear.
Okay, very good. So then, okay, there are no MZVs. Okay.
Okay.
Sorry.
How much time I have? Just to understand. I didn't remember when we started. 15 minutes? I started at 15, so half an hour? 29 minutes exact? Okay. Let's say 29 minutes. I like it. So let me erase this stuff. So now I want to give you, not directly the proof, let's say, proving this stuff is a super tedious computation. Integrals are horrible. We took like months to do it, and also our soul was drained by this computation. At least mine, for sure. At some point, I had enough. And so I'm not going to repeat this stuff because I don't want to have the trauma again. So I will be very schematic at the end. But I can be a bit more precise in a warm-up example. The warm-up example is exactly what I was mentioning before in the first lecture. So we know this f, mat BBF, from localization that is proportional to some derivatives of w and is related to the BPS part of the 4-point function that we are looking at, okay? And in principle, there is a way, using conformal perturbation theory and all this discussion that I'm doing about deformations, insertion of operators, and so on, to prove this one just looking at integrability and the cusp, okay? But this is a warm-up example because the same logic will be used to prove this one, okay? Cool. Warm-up for CBPS. So, I'm not repeating the same formula that is there, but the setup is similar to the one I was showing before. So we have a line from minus infinity to infinity, and then 2 points. The point T1 and the point T2. And we have the standard line with phi parallel, so the standard 1/2 BPS line, before and after this segment. But in the segment, let me do it like with a double line. We turn on the theta angle. So we have cos theta, phi parallel, plus sin theta, phi orthogonal. Ugh. So you see at the end, all this discussion of var phi is totally useless because I'm not using var phi anywhere. But anyway. No, var phi, no, come on, whatever. Okay. No, okay, let's stop, please. Otherwise, in the seminar on Monday, I'm writing spin as J, so please. Okay, so the setup is this one, but there is something more respect to before. We are inserting operators in T1 and T2, but some special one. So we have phi parallel here, and phi orthogonal 1, because it's the one that we choose at the beginning. You remember from the cusp picture. And in the point T1 and T2, we put something that is orthogonal to phi parallel, but is also orthogonal for phi orthogonal 1. So we put phi orthogonal. I had to stay silent, but anyway, phi orthogonal 2. And here again, phi orthogonal 2. Okay? So normal line, phi orthogonal 2, theta angle line, phi orthogonal 2, normal line again. This is the setup that we will use also after. Okay? And this object, let me call it W theta, and is equal to, you already know, let me write it as a trace, like a trace of the segment with theta equal to 0, phi orthogonal 2, the segment with theta on, phi orthogonal 2, and the segment with theta 0. Okay? Cool. So when theta is equal to 0, means that in the segment there is only phi parallel. So it means that the line is the normal line with 2 insertion. But you can recognize it because this means normal line with insertion of phi parallel, phi orthogonal. So it's the 2-point function of the tilt operator, the one that we were studying before. So it means that for theta equal to 0, this is actually the 2-point function of phi orthogonal 2, that we already know what is it. Because we know this is like a 2 Bremsstrahlung over t, 1, 2 square, okay? We computed before. But then when theta is non-zero, the vev of w theta behaves like usual, like we were saying before. So it will be proportional to some number over t1, 2, and there is an anomalous dimension. Because we have some flavor changing operator, so there are 2 cusp, if you want, and again, as before, there is some cusp anomalous dimension, but this time there are operator inserted, so let me call it gamma 1, because in any cusp, in any point that is actually a cusp, we are inserting an operator of power 1, so a dimension 1, okay? But why this is cool? Because again, integrability can compute gamma with insertion of operator of power L. So we can compute from QSC the configuration in which, again, this is the general one. In the tip here, I'm putting phi orthogonal, if you want, 2 to the power L. And it's exact again. It can be written at the determinant, etc. We are just looking at gamma 1 now. And you can imagine what is going on. The gamma 1 can be expanded in 1 plus sin theta square. And again, as an analogy of before, the Bremsstrahlung, but this time is Bremsstrahlung 1. So the Bremsstrahlung knows about the charge of R symmetry inserted in the tip. Okay? And this again is a very well-known function. Is again a ratio Bessel function, but this time the Bessel function is some kind of modified with a theta angle inside, not in the. It's very weird. It's just like before with some theta deformation of the Bessel function. That's it. Cool. And so what is the game here? The formula, the important formula is that if we do the derivative respect to T1 and T2 of the log of W theta over W0, okay, this is equal to minus 2 B1 over T12 square sin square theta plus corrections. So this is the formula. Here we know it from integrability, from the expansion of gamma 1, and this one is just the double derivative of the log of the 2-point function of before. That we can try to play. We can expand it in theta 2 and build in the integrated correlator from this side, and then compare it with the right-hand side. Okay? And this I try to do in 2 lines. It's pretty simple, because the log we expanded in sine theta, as I was saying. Like the sine theta square term of this log is an integrated correlator of what? Sine theta means 2 power of theta, so means 2 fields. But we already have 2 fields inside. So we are trying to do in a 4-point function using the fact that we have already 2 external points. So it's a 4-point function with 2 points that are attached to a derivative. So it's an easy way to insert a 4-point function in the loop. So we have the phi orthogonal 2 in position T1, and T1 is fixed. We don't integrate on it. Indeed, we integrate in, let's say, S1 and S2, but then expanding in theta means that we are taking down from the action phi orthogonal 1, okay? And this is in position S1. Then there is phi orthogonal in position S2, 1 again, because obviously the operator will be inserted here, S1, S2. So we are building our 4-point function, phi orthogonal T2, that again is fixed. Okay? Then there are plus some counter terms, like a 3-point function, etc., that all of them are not depending on T1 and T2. They don't have a logarithmic divergence, so we don't care. We can drop them. And so it's simple like this. This log is an integrated 4-point function, and we just have to act with the derivatives. Okay? But this means, let me rewrite it in a nicer way, if you want, that derivative T1, derivative T2 of the integrated 4-point function over the W without insertion is equal to minus 2 B1 over T12 square, yes, T12 square. And this is our integrated correlator, again. So just in a few lines, starting from a setup that is very nice, let's say, and acting with the 2 derivatives, we have a 4-point function integrated equal to a function of g that is known, exactly. Cool. But what we can extract from it, let me just, I lost, okay. Yeah, where? Ah, okay. Say it again. Small theta, phi 0. The beta square, huh? Theta square, okay, sorry. Yes, but I'm not expanding in theta. This is why I'm expanding in sine theta, because I exactly want just phi orthogonal insertion. And I'm just expanding that one. But then later, for example, at higher order, you will start to see something that is coming from phi parallel. Why? Because indeed phi parallel is cos theta. I can write in a square root of 1 minus sine theta, but expanding this one will start to appear at higher order. And this is happening later. I can show you very precise statement on this, but I guess it's a bit hard on the blackboard. Thank you. Okay. So what is the point here? The point here is that the 4-point function, we know this 4-point function exactly. So we can write it in terms of x, we can integrate it, and we can find a very interesting situation that will be proportional to f. Again, this is f of x. So this f of x is appearing also here. And so what we have to do, there is very briefly, let's say this integral is super simple because it's a total derivative of f. That's it. And so what we have to do, compute f in the extrema of this integral. And this is giving us some very nice constraint, that is so the integral is indeed this f computed in the extremal point of the integral. And this is giving f bold, the infamous f bold that we like, minus 2 equal to b1, that is in the right side there, actually multiplied by b here, so I'm putting here in the denominator, okay? Because from this integration, f is appearing and b is appearing. B is the normal b, so b0, the one of before. This is the one with the insertion of the tip, okay? But we know what is f, because f, from the analysis of before, we know that is 1 plus CBPS. Okay? And so, just looking at this integrated correlator, we can conclude that CBPS square is 1 plus B1 over B0 over B. That's it. And so this is coming from information purely from integrability, because B1 is just captured by integrability. There is no other way to have it. No, okay, there is another way to have it, indeed, again, losing localization, but say, you see what I mean, in the sense like there is a dichotomy, you can do in one way or in the other. We just use integrability data now and integrability kind of thinking to arrive here. And what is the interesting point? And indeed, B1, we know it exactly. So, and with this formula, we can also prove that since f is written in terms of derivatives of w, we can see that B1 is, let me be precise because this formula is nice, is 3w second over w prime minus 2w prime over w. That's it. And this is known. This we know that is true. And we prove this formula that we already knew before, just passing through this setup through integrated correlators. And we are fixing CBPS in the same time. Okay? Cool. So I have like a bit more than 10 minutes. I try to, starting from this warm-up example, the logic is exactly the same. We go hardcore. So we want to go theta to the 4 and go like a hardcore to prove this combination here. Obviously, I'm not going hardcore at the blackboard, just the logic. But maybe I'm leaving it because they are nice. Let me erase it here. Cool. Okay, yeah, so with this warm-up example, with the same setup, we repeat theta to the 4 and see what is going on. What is the problem here? That we cannot do the same kind of computation of before, saying like, let's integrate this stuff randomly, regularizing the integral. Okay, there is some kind of divergence. Who cares about the divergence? Okay, see you. No, because now we have to go to higher log power, so we really need to regularize properly and be very careful. And the best way to do it is to think about this, all this business as a conformal perturbation theory. So It means that my Wilson line, path order exponential, blah, 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 blah. I can interpret this object here as the action of a CFT, okay? So, imagine that you have the action of a CFT that we theta deformed like before. So there are some pieces of the theory somewhere in a segment where there is theta, and some other pieces in which there is not. And we can think about like the general action with theta as the undeformed theory with theta equal to 0 plus a deformation, delta A. Okay? And this delta A obviously is related with, if you want, you can write as a density of Lagrangian, is related with the insertion of some density of the Lagrangian. Okay? And since we are a bit skeptical, we are very careful of which kind of action is delta A. Okay? Because if you start, this is something related with what Diego was saying, because we know what is our action, our Lagrangian, if you want. That is integral of the t of sine theta. I'm repeating always the same formula, but just remember it. Plus cos, but cos is square root of 1 minus sine square. Phi orthogonal 1. Okay, so one naively can say, okay, this is mine action. I simply expand in theta and will be okay. Kind of no, because we have to take in account also, for example, the action of the identity. The identity is actually inserting a 1 over epsilon term, and we use it as a regulator. And then our conformal manifold that is generated by this marginal operator, where are they relevant? So the relevant are contributing, we don't know, but so we are super skeptical, and we are considering all the operators possible, and we do the most general action possible. Okay? So delta A, taking advantage of this kind of stuff, we can say will be sine theta. So there is only one sine theta term, there is only one sine theta term, and there is only one operator, and we keep just one operator here. But this time we call it O phi parallel, because this is the real one-dimensional, from the conformal manifold point of view, this is the real operator. It's not the field. The field is something, the real operator in the 1D CFT is another stuff, but it's related to it, okay? And plus, since we are skeptical indeed, kappa is from 2 to infinity, there are all the other orders in theta that are starting from 2. So you can see now how complicated it can be. There are some coefficient. Now I'm explaining all the definition. Just give me 1 second. O of delta n. In t, obviously there is an integral here. Cool. So this part is pretty clear. So we have our marginal operator that is generating the CFT manifold, and will remain 1. It's only one operator of dimension 1, and this is a brother in the real 1D CFT, not as a field, okay? And then there is a plethora of other operators that are appearing at different powers of kappa, of sine, okay? With some Wilson coefficient B, this is depending on the indices, and then there is a regulator. This is the same regulator that is appearing in the cusp. This is very important, because then we are doing the connection with the cusp. So this is a UV regulator, and the power is delta n for dimensional reasons. So we have to have this power to make this stuff with non-dimension, okay? And then O delta is any operator you want in the 1D CFT. Cool. And now the logic is the one before. So the integral, sorry, the Wilson loop deformed can be seen as a expansion in theta of insertion of this new action, okay? This very complicated action. So this can be written as the integral in the t of path order exponential blah 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 delta L, and then double integral of path order exponential blah blah double L, and so on. Actually, this is not very correct. Let's say double bracket, I mean insertion on the Wilson loop. Here we are in the conformal manifold. It's more like the insertion in the proper 1D CFT that we are considering, the most general one in this picture. But let's say these are subtlety. But I mean, we can expand, taking at any order down one Lagrangian insertion, and so on, and so on, and so on, and so on. And this is the logic, and we are applying it with the same setup of before. I guess since I have like a 7 minutes, yeah. Thanks. Yeah, and then indeed, since I have like a few minutes and I want to show you also some pictures because they are nice, I just, let me say, skip the technicalities. But the point is that the setup that we use for the warm-up example, so line with undeformed part, deformed part, and undeformed part again will be related to the Kasp anomalous dimension. But this time at theta to the 4. So it's a bit more complicated. We have to expand this action this time. This action contains unknown parameters. And this time, indeed, as Diego was saying, for example, we have to consider insertion of the identity. So we have a 1-point function, 2-point function, 3-point function, 4-point function with all the identities inside. And then all the mixed one with the marginal operator, 2-point function of the marginal, 3-point function of the marginal, and unprotected one or delta with a sum. So it's a crazy situation. So we have a huge list of integrated correlator to check. What is the point? That there are some rules. So those sums, it's impossible to compute all of them. So what you have to find? We have to find 2 conditions to eliminate the sum from our setup. So the setup that I was talking about before. So just schematically, line with 2 cusp and theta angle here, this will be compared with the gamma cusp expansion, okay? As before, exactly the same. This is giving some kind of a equation, let's say. We have to compare with another situation in which we are saying the empty line with insertion on top has to be the same with the line totally deformed with the same insertion on top. So they have to be the same. The wave of the Wilson line that is totally deformed or non-deformed with insertion on top has to be the same. The wave has to be the same. And this is giving another equation. And then we can eliminate the sum. For example, this is giving us that the sum of V, again, very schematic. You know, 3-point function are starting to appear here. Anomalous dimension are starting to appear. It's very complicated, but this big sum is equal to the integral. And here we are seeing the integrated correlator of df over x cube times another kernel, whatever, plus numbers. We have this formula. And here we have another one that is saying, if I find it, that is saying, remember, we are comparing with the cusp here. So Bremsstrahlung plus curvature, this term here, so sine to the 4 expansion is equal to the sum Bn Cn over delta 1 minus 1, that is the same, that we don't know how to compute it, but now, yes, minus again the integral of delta f per times some kernel. And what is going on here? We have 2 equations. We take this sum, plug it inside here, put everything together, and what we find exactly this combination here. So we have the 2 combinations with the plus and with the minus. We can disentangle them, and finally, after a super tedious set of integrals, we can prove 1 and 2 independently. Okay? And I guess this is my take-home message. So integrated correlators are difficult to prove because you have to rely on conformal perturbation theory. They are kind of complicated even on the line, but the power that they have in numerical conformal bootstrap is crazy, so it's worth it to inspect and go higher, for example, maybe indeed looking at 6-point function, looking at different integrated correlator for different spectra, for example, for different 4-point functions. So this is just one. This G and F is just related to the simplest 4-point function, but in principle you can do more. And so, just to conclude, I have 3 minutes, I guess, no? Can I show a few pictures? Thank you. Yeah, so let me... Okay, can I go back? Yes, I can go back. No, it's fine, I don't need to point. So this is just to wrap up and show you some real stuff. This is the spectrum. Those are the 10 states that I was mentioning. You see here, well, come on, they are almost the same. It's perfect. And then the dotted line is the 07 one, the one that has parity negative. And this has to be eliminated from the spectrum. And this clearly, it's very clear here that when you go very strong coupling, for example, a G equal to 4, that in lambda is very strong coupling, not like super very strong coupling like Kolya is doing now with Simon, but kind of very strong coupling. You see that without this line there, the one that is going to 7, the gap is very big at strong coupling. So we have a very good gain from this discussion that I was doing about the functional that is exploring negative values, etc. Then one stuff that I wanted to show you is that just adding the first example that I gave you, two data from integrability, so delta 1 and delta 2, you just plug in STDBP and this is the result you have. This is not a function, those are actual bound, so this upper and lower bound together, but the precision is that good that looks like a function, and that obviously this is interpolating with no data, and is impressive enough, I would say, that is going to 4 digits of precision. Some bad point has 2 digits of precision, but that's fine. We can go higher, indeed, adding more data from integrability, and you will have actual bound. Those are pretty clear that they're bound. But again, there is some powerful stuff happening now, that indeed you can use parity to do the stuff I was mentioning before, so eliminating this 07 operator. And those are the error plot in logarithmic scale, and you see that the dashed line is the error before, and the normal line is the error after parity. So you gain 2.5 times the error, so it's pretty big gain. But, sorry. Yeah, okay, this is how it was, and I just want you to compare when you add correlators, like integrated correlators, this is very powerful part. Then this is one constraint that is really shrinking the bounds in a very clear way, just one constraint, or 2 or 1, either 2 or 1. And then when you put all the 2 together, it's extremely powerful. It's still very weird at coupling, but we are okay with it. It's fine. A strong coupling is impressively good, so let's look at the right side, and don't look at the left-hand side, it's fine. Okay. Then, okay, this is just because we took like 3 days to do this image. But this is the C1, so the first OP coefficient, and any of this magnification is one step more in implementation in STBP. The first one is just 2 states, and then we add 10 states, and you see that the blue line, you have to magnify 25 times just to see the new bound. Then you magnify, you see the green one inside, you magnify 25 times, and this is just one integrated correlator, and inside there, it's not easy to see, but inside there, in the green one, there is another bound, another upper and lower bound, that is just adding the 2 states. So we pass from 10 to the power 2 at the beginning to 10 to the minus 8, just adding the 2 constraints and 10 states. Okay, this is very powerful for the lowest line OP coefficient. And then just to finish, I wanted to show you the 4-point function computation, because come on, it's amazing. It's nice because you can see clearly, okay, this is the 3D plot of g of x, so this function here, the full g of x, as a function of the coupling that is going from 0 to 4, and as a function of x. So for any x, if you remember, I was saying that I was computing STBP for x0. So you put x0, you compute the point, and then you put another x0, you compute the point, and so on and so on and so on. You build the whole 3D plot. And what is nice here is that you can see clearly the crossing symmetry, because it's a parabola, and the crossing symmetry, this one, is actually visible in this picture, okay? And the same for f of x, the reduced one. That, remember, has the crossing symmetry with a minus, so clearly has to be this sinusoid kind of shape if you slice it along for a fixed g. Yeah, those are slices for fixed g as a function of x. And again, any of these line is not just a line, it's an upper and lower bound, and any of them has a crazy precision. And this is the last slide I wanted to show you, that is indeed the precision that is going from 10 to the minus 14 to 10 to the minus 6, 7. And yeah, this is just the last stuff I wanted to say. I guess I'm late of 3 minutes, sorry.
Can you, what can you compute without Bootstrap directly from integrability? Is this correlator given by some hexagons, for example?
Oh, this I don't know. I can, for sure, without numerical Bootstrap, you mean? Or,
yeah, for example, I remember Shota vaguely. I thought this was computed by 2 hexagons because it's an open, it's a disk.
Yeah. Can you pass him?
We have, so one loop is what shot with hexagons, then wrapping starts, but we can do analytic bootstrap for 2 more coefficients.
Yeah, when he did we coupling up to G square, we can, no, up to G8 we go. It was completed the G square term, and just using analytical bootstrap, that is something I didn't mention here, but obviously you can do the same stuff with analytical bootstrap, you can push it to G to the 8.
I see. What's the obstacle from Shota's point of view with hexagons to just...
I don't really know, like going higher, you mean?
Yeah.
I don't know the technicalities.
If I understood, you need to do something with boundary reflection there.
Yes.
And just like kind of, they were not very sure what to do, I guess.
But now that you have this data, can't you just...
Well, I can't, but maybe Shota can. Or you.
What about SOV? Are there SOV expressions for this correlator?
I don't think so.
Or
There is
for the
no
3-point
SOV,
functions?
at least from what I know, no SOV interpretation. Yeah, and some for some group.
Mm-hmm. Would this be a good setup to try to develop SOV? It looks so simple.
Why not? But I guess it's pretty hard with the open boundary, because the line is open. Yeah, for sure.
Okay.
Fine. Maybe I didn't understand completely your method, but the question is the following. So we have g of x when x goes from 0 to 1, but can you efficiently, in principle, bootstrap it when x is complex? I mean, complex, but as analytic continuation.
Okay, this is something that we actually wanted to do, yes. And then at some point we were bothered about the paper and we published the paper without it. So we never tried, but in principle, yes, why not? I mean, you can choose x0 to be what you want, in principle. I don't see any obstacle to go complex, but we never actually tried.
Yeah, so you can take real part of 4-point function, and it is still a linear function of structure constants, right?
Yeah.
So you can do real and imaginary separately. It's still the same class of objects, which bootstrappable. Yeah, well, I think...
yeah, it is fancy, yeah? It is fancy.
Should be careful to go too far, but yeah. You can try. Because at some point this exponent will actually start being bigger than 1, I think.
You mean the second exponential decay?
Yeah.
Yeah.
Absolutely sure. Well, if you are sure with some confidence that there are no more integrated correlator, like for example, you imagine
not a disorder. A disorder, I'm confident that there are no more.
I mean, I see. And why you know that?
But because we tried the only other possibility to integrate the 4-point function. Indeed, what is happening, the warm-up example that I showed you, that the other possibility of inserting 4-point function in different ways give you a total derivative. Since you have a total derivative, this is related with the warm-up example, the CBPS one. And so I guess a disorder is just fixing CBPS and the 2 independent constraints. But I would say that maybe a next order, maybe the constraints are, I don't know, 75, I don't know. It's unclear, sure, but... Yeah. Yeah.
So, okay, very good. So this was assuming that you want to extract your information from gamma cusp.
Yeah.
But imagine that you know other deformation of
yeah, sure. For example, if you squash,
yes.
you put this stuff on some weird shape, you squash, you have a new parameter. Why not? For sure.
But you don't know if.
But again, for example, any deformation, again, at leading order, is still Bremsstrahlung. So at that order, for sure, anything you do, any deformation you do, you will have the same stuff, blah, 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 equal Bremsstrahlung. If a next order will be different, I honestly have no intuition, but could be that indeed if you're putting on a squash sphere or like some weird stuff, maybe something can be done.
So there was also unexplored, I guess, or maybe already explored option in the paper of Amit and Lyon to do conformal transformation of the line and then expand it back around the flat line. So this another type, or you can combine with some cusp and then do conformal transformation.
They say comparing with cusp is very cool because you know exact objects.
But like Amit and Liang, they claim there are infinitely many integral constraints, right?
Even on this situation?
On 4-point functions. It's approximate claim.
Infinite minus 10.
Very good. So let's thank Michelangelo.
Thank you.
So, and like I said, so we have now informal discussions in the afternoon, but I think as far as the official program goes for this first week, we are done. So thanks a lot everyone for coming. Very good.
And we should thank the organizers for this opportunity to discuss and learn.
Yeah.
Sorry, we forgot one thing. So if you are going out of the room, please come back in. And we are going to get we are going to take a group picture now. Con a Luis vai ficar melhor. Eu acho que a Luis vai. Ah, sim.
Okay,
Ah.
let's come to the front, please.
Okay, thanks.
Something is actually monotonic.